Welcome back, AP Statistics. This is an additional topic, test statistics again for a 2 proportion z-test this time. We had an additional section a little bit ago about test statistics for a 1 proportion z-test. Now let's talk about how it works for a 2 proportion z-test. Recall that a test statistic computes the number of standard deviations of a particular sampling distribution. A sample statistic is away from the proposed value for the corresponding parameter. Now, what does that mean? Test statistics for the population mean and proportion fit this form. Here is what I'm talking about. I have in my denominator the standard deviation of a sampling distribution, and the numerator is the difference between a sample statistic and a proposed value for the parameter. In this case, it would be the sample statistic p hat minus p sub 0, all right? And that divided by the standard deviation of the sampling distribution of sample proportions. That is the difference of 2 sample proportions, sort of. Here is the test statistic for a difference of proportions. Now, there are a couple things that may stand out to you. You may be wondering, what is p sub 0? Well, if you recall, p sub 0 is 0. In any hypothesis test we do in this class regarding 2 proportions, p sub 0 is going to be 0. That is, there is no difference between the 2 proportions. And we test to see if there is a difference one way or another, or almost all the time it would be a 2-sided alternative, if there's some difference between the proportions one way or another. So that's probably the first thing you notice, that there's no p sub 0, and that's because p sub 0 is equal to 0 for our intents and purposes. If you're really paying close attention, you'll recognize that the denominator is not the same standard deviation of the sampling distribution for the difference of sample proportions. It's slightly different, right? So not only do we notice that p sub 0 is 0, all right, because the null hypothesis says that the proportions are the same, but we also notice that the denominator looks a little different. It is slightly different than the standard deviation for the difference of proportions. The reason why is beyond the scope of the course, so you do not need to know why, and to be entirely honest, I don't even know why. Moving on. We need to talk about what p hat and q hat are, because in this chapter, p hat always seems to be followed by a subscript of either 1 or 2. So what's just p hat with no subscript in the context of 2 proportions? Well, p hat with no subscript is the proportion of successes of the 2 samples combined, all right? So if we let x1 be the number of successes in the first sample and let x2 be the number of successes in the second sample, p hat is the sum of the x's over the sum of the sample sizes. So there you go. There's p hat. Q hat is, of course, the complement of p hat. So whatever I get for p hat, subtract it from 100%, and you get q hat. Let's do an example now. Suppose 1,000 berries were picked from each of 2 bushes, so 2,000 berries total. The number of berries on the first bush that were partially eaten by bugs and must be discarded is 55, while the number of berries on the second bush that must be discarded for the same reason is 76. We're going to find the test statistic for the set of hypotheses null, p1 minus p2 equals 0, and alternative, p1 minus p2 is not 0. And then we're going to use the test statistic to compute a p-value. And we need to remember, for a 2-sided alternative, we are going to use 2 times the normal CDF. So at this point, it's a bit of plug and chug using the formula at the bottom right-hand corner of the screen. Now, some of you may be wondering, why can't we just enter this information into our calculator? Well, there's a reason for this. You can find both the test statistic and the p-value given the information we have. However, that's not what we're practicing doing. You may be asked about how a test statistic is computed. There are problems about that. Or how to compute a p-value using the statistic. So we'd just be given a test statistic. How do you compute a p-value? You're familiar with that. And we need to remember we're working with a two-sided alternative, so we do 2 times the normal CDF of all our usual inputs. But because of what we're practicing, we're not going to take the easy route of just putting things into 2 prob z-test and having the calculator do everything. All right, I want to prepare you for everything that you might see. So we're going to let P1 be the proportion of berries on the first bush that need to be discarded, and we're going to let P2 be the proportion of berries on the second bush that must be discarded. Then our z-test value is this complicated mess right here. Let's break this down. So first we need P1 and P2, rather P hat 1 and P hat 2, our difference of sample proportions. Our first sample proportion is 55 out of 1,000. Our second sample proportion is 76 out of 1,000. So right off the bat, we should be expecting a negative number. So we're hoping to get a negative number, and in fact we do. The denominator is by far the more interesting part. So let's look at that. What is P hat? Well, P hat is going to be 55 plus 76 over 1,000 plus 1,000. It's my total number of successes over the total of the sample sizes. And then I have 1 minus P hat, which is Q hat. So here's P hat, and then this difference right here is Q hat, all right? And then I have 1 over my first sample size, 1 over my second sample size. You could have written 2 over 1,000, but explicitly writing the 2 1 out of 1,000s makes the point clear, because technically the sample sizes could be different. If you were to evaluate this, you get negative 1.898 approximately, so a little shy of a negative 1.9. So what kind of a p-value would that get us? Well, we would do 2 times normal CDF, because this is a 2-sided alternative, and we would say normal CDF, negative 10 to the power of 99, negative 1.898, 0, and 1, all right? And that would get us 0.058. We double this value right here. That's how we get the 0.058. If you were not to double, if you tried to do this on your own and you got 0.0229 approximately, you're going to need to double that. Just remember to do that, and you are good to go.